Okay, we finished up the section on periodic properties, the chapter, I guess, unit, whatever you want to call it. Um, I guess we need to move on to a new chapter. I was hoping to kind of do this when we're back at school, but I don't. Here we are. Um, so let's get into chemical bonding. Um, this is understanding bonding is really the reason we went through. Well, one of the many reasons we went through all the quantum mechanics and periodicity stuff. All that comes together and explains how bonding works. Um, we had things like Dalton's model with atoms are little marbles, but how do they bond together then? What holds them together? Just forces. They didn't know. Um, Now that we have a firmer understanding of electron clouds and electron configurations and all that good stuff, we can kind of start figuring out how bonding works and why atoms bond with each other in covalent and ionic bonds. So let's get into that. This is pointless. I'm going to cut that out when I do my own PowerPoint. Notice now, yeah, we're back to the book's PowerPoint on this. I will, as we go through this chapter, supplement with my own PowerPoints. I'll upload those as well, so you can look at those. But for at least this early in the chapter, what they do is fine. Now, blah, blah, here we go. There's many different bonding theories. There's not just one grand theory of all bonding everywhere. We got a number of different theories. The theory that we are going to use here is Lewis theory, named after Gilbert Lewis. But the idea is a good bonding theory is going to have to predict why they bond together, why they combine in certain ways, why it's H2O and not H3O or something, why sodium chloride isn't NaCl2. The theory has to obviously explain why they do that. But also it's going to have to explain why the molecules have the shapes they do. So we're going to have to get a little bit into what we call molecular geometry. Why is a water molecule bent at an angle, whereas a carbon dioxide molecule is linear? It's not just an abstract thing. It affects their properties. If water molecules were linear, it would be a gas at room temperature and not a liquid at room temperature. And obviously that would have bad consequences for us. So bonding theory, a valid bonding theory is going to have to explain all of this. Your book only gets into Lewis theory. We're going to go through that, and then we're going to look at some more advanced theories on our own because we can do better than what they did. So yeah, Lewis theory basically looks at the valence electrons. Remember, those are your outer shell electrons, not the core electrons. So for the most part, all your noble gas core electrons are buried inside. We don't care. All the d electrons are buried deep inside. We don't care. It's just the outer shell S's and P's that matter. Okay, so what Lewis decided to do, and this is back in like the late 1800s, was, or maybe early 1900s, but write the electrons as dots, only the valence electrons. So you'll draw the electrons as dots around the symbol for the element, and that's going to be something we call a Lewis dot diagram, and we'll build Lewis structures out of those. Okay, so for any of our main group elements, remember those are the ones that are not transition metals. So the alkali metals, alkaline earth metals, and then the P block on the other side. You're basically going to draw dots for their electrons. So taking oxygen, 1s2, that's your core, ignore them. Your valence shell, 2s2, 2p6. You've got 6 valence electrons to work with, 4 plus 2. So you're going to draw those as dots around the symbol for oxygen, O. Now, notice how we do that. There's 4 sides, top, bottom, left, right. There's a total of 2 plus up to 6, so a total of up to 8 electrons to work with. And we know because of the orbitals that they pair up. So we use each side essentially as an orbital and wrap it around the symbol for the atom. So notice you have 4 plus 2 is 6 electrons. 1, 2, 3, 4, start pairing up. 5, 6. So notice you go around filling in 1 electron at a time and then pair them up if you need to. Essentially following Hund's rule. Although notice I'm playing fast and loose here because I'm mixing the S's and the P's together in doing that. That's what we do. you don't leave them unpaired or paired as they would show up in here necessarily, although oxygen worked out right anyway. You unpair them as much as possible. Now, that obviously means that what we learned with our configurations isn't applying exactly here. And there's a reason for that that we'll get into later in the chapter. But yeah, the general idea is count up how many valence electrons you have, whether they're S's and P's, doesn't matter, and then distribute them around the symbol for the atom, the element, one at a time, unpairing them as much as you can, and then going around pairing up as you need to. Okay? So they say that here. You fill the dots singly first and then pair them up as you need to. The only exception is helium, because 1s2, it's a full shell. Those two pair up. Of course, you won't have to worry about that because there's never anything that's going to bond with helium. It's a noble gas. It's inert. It doesn't react with anything. So notice here, lithium, going across the second period, lithium 2s1 has one dot. Beryllium 2s2. So there's two valence electrons, one here, one there. Notice again that disagrees a little bit with what we learned 2 chapters ago, in that we would expect those S2s to be paired up. And in fact, they are in the way we read our configurations. But for some reason that we'll get into later, when atoms are preparing to bond with each other, they rearrange their electron structure. And so those two electrons end up being unpaired here in beryllium. Same with boron, S2P1. By all rights, two of these should be paired up, but in the Lewis structure, you do not do that. You unpair them as much as possible. And so this structure as written is correct. Same for carbon, nitrogen, and so on, right? And neon, you'll notice it's all surrounded, all filled with electrons. S2P6, there's your 8 electrons all around it. No more room for electrons, it's full. That full valence shell, by the way, is always 8 electrons, except for helium. So we refer to that as an octet. Before they even knew about S2P6 configurations, they knew that 8 electrons did the job, made it a stable configuration, and it was full. So without knowing why, they called it the octet rule, that atoms prefer to have 8 electrons in their valence shell. Neon has it, so it's stable, it doesn't react. Fluorine just missed it, so it will react with anything in sight to gain 1 electron and get to neon's configuration. Okay, so oxygen missed it by 2, it will react to form a 2 negative charge. Fluorine picked up only 1 electron, had a 1 negative charge. Okay, so that's that. The fact that every atom wants to get 8 electrons in its valence shell is again called the octet rule. Now, the sample problem is, although it's kind of trivial, write the Lewis structure for phosphorus. Well, you look at the electron configuration. Phosphorus is an S2P3, total of 5 electrons, so you draw them. 1, 2, 3, 4. Now I got to pair up for the 5th. And there you go. Now, helium, a little weird because, again, 1s2, those electrons, that's a full shell right there. And so you pair them up to show that helium is not going to react with anyone. Sometimes we refer to that as a duet, or the duet rule, although not much of a rule, it only applies to one element, helium. So every element wants to have 8 electrons in its valence shell. If it doesn't, it's going to do a chemical reaction to get to 8. The exception is helium, which only needs 2 in its shell. Also, hydrogen only needs 2 in its shell, although it doesn't have a duet, it only has 1. So when hydrogen reacts, it's only going to go for 2 electrons. Everyone else is going to go for 8. Helium already has its 2, it's done. Noble gases already have their 8, they're done. Now, a chemical bond is the force that holds atoms together in a molecule, or even not in a molecule, in an ionic compound. There's 2 types of chemical bonds, which you learned about in middle school, I'm sure. Ionic bonds and covalent bonds. In an ionic bond, just to recap, an ionic bond, one atom takes electrons from the other. So we say there's a transfer of electrons. Chlorine's going to take an electron from a sodium, forming Cl- and Na+, and they stick together because of static electricity. Covalent bonds are sharing electrons, where they overlap their electron clouds and share the overlapped electrons. Before the whole virus thing, we kind of talked about how it's more, rather than a sharing and being happy thing, it's more of a tug of war. Both atomic nuclei are pulling on those electrons and trying to take them for themselves, but neither atom is strong enough to do so, and so you end up with a default sharing. So that's the two types of bonds, ionic and covalent. In either case, you go for the octet rule. You're going to gain or lose electrons to get to 8. You're going to share electrons to get to 8. So, let's look at ionic bonds because that's the easiest thing. We'll only deal with this on a couple of slides, and the rest of the chapter is all covalent bonds. In an ionic bond, you have a metal and a nonmetal reacting. We'll qualify that more precisely in an upcoming lesson. But for right now, metal and nonmetal. I'm not sick, by the way. I just have some allergy postnasal drip going on. Metals, you'll recall, have very weak attraction for electrons. Nonmetals have much stronger attraction for electrons. And so when you get them near each other, the nonmetal is going to be able to pull electrons away from that metal. Why would it do so? Because remember, those nonmetals like fluorine, 1 electron short of a full shell. It's going to want to take that electron from the cation, from the metal. Metal, well, sodium has 1 electron in its valence shell. To get to 8, it would have to gain 7. Well, that's a lot of electrons to try to gain. Not to mention, it's got a weak attraction for electrons, so even if it wanted to gain 7, it's not really able to do it. So, bottom line is your metals with weak attraction and small numbers of electrons are going to easily lose them. When they lose them, they go back to the previous shell, which is already full. And so they get a sneaky way into getting their octet. The nonmetals have strong attraction, and they're just 1 or 2 electrons short of a full valence shell, much like Amelia. And so they're going to use their strong attraction to gain those electrons and form negative ions. Now, you'll notice once they've done that, say a sodium atom gives away its electron, 1 plus charge, it's a full shell, it's happy. Chlorine atom gains an electron, 1 negative charge, it's got a full shell, it's happy. As far as they're concerned, they don't need each other anymore. Sodium atom, chlorine atom, now ion, are both stable. So why do they stick together? Well, they stick together because now they have opposite charges. And even though they don't need each other anymore, they both have their stable configuration, the positive ion and the negative ion attract each other and they stick together. So that's ionic bonding. It's really easy to follow. It's really just gain and lose electrons to get a stable shell, and opposite charges hold them together. Real quickly, how you show that is there's the dot diagram for potassium, there's the dot diagram for chlorine. Notice 1 electron, 7 electrons. So you bring them together and you show that this guy's electron went to that guy, and now potassium lost its electron and has a plus charge. Chlorine now has a full octet of electrons and has a negative charge. Notice it's isoelectronic with a noble gas, and now it's happy. Is potassium really happy like this? Yeah, because we're showing no electrons, but remember, that just means the previous shell is the outer shell now, and it's already full. So it's got its full octet, it's isoelectronic, also with a noble gas, and so it's happy. So both have reached stable configurations. Notice the little brackets there so we don't overlap the negative and the dots. But they both have stable configurations, and they're happy with the way they are. But now they stick together because of opposite charges. And that's ionic compounds. I'm going to give you some textbook problems to do tonight, just to practice, drawing dot diagrams mainly and showing the transfers here. Tomorrow we'll look at covalent bonding, at least the introduction to it, and we'll form some single, double, and triple bonds. And that's good for today then. See you tomorrow.